You said that China was winning the AI race, the AI competition.
Something was revealed 3 weeks ago that Silicon Valley didn't want to hear. It was one single sentence that exposed the truth of how the AI race will not be won by faster GPUs, but by changing how computation itself works. But before we dive into it, make sure to subscribe to our channel for more innovative tech breakdowns. The statement that shook the AI world.
China has twice the amount of energy we have as a nation.
I want to ask about that.
Twice as much energy as we have as a nation, and our economy is larger than theirs. Makes no sense to me. If you want to build a data center here in the United States, from breaking ground to standing up a AI supercomputer is probably about 3 years. They can build a hospital in a weekend. That's a real challenge.
When Jensen Huang recently spoke at the Financial Times AI Summit, most people were expecting the usual optimism about innovation, scaling, and the future of GPUs. But instead, he delivered something to the audience that was far more unsettling. He simply said that China is going to win the AI race against the West. It will be possible not because of better software or copied hardware, but it will happen because the foundations of modern computing are reaching their limit, and China is on a path to build something fundamentally different. If it was said by some Chinese representative or anyone else, it could have been ignored. But coming from the CEO of the company that is responsible for powering almost every major AI model on Earth, this was not marketing or exaggeration. It was actually an admission of how far ahead China is in this race. NVIDIA's success is completely based on computation that has been pushed to its maximum physical boundaries by having more transistors, higher power draws, and larger data centers. This model has worked brilliantly for the past several decades, but now the cracks in it are becoming impossible to ignore. For years, governments and analysts believed that AI dominance could be controlled by restricting access to advanced chips. They banned the fastest GPUs, blocked the smallest manufacturing nodes, and limited access to extreme ultraviolet lithography for China. The assumption here was simple, that without cutting-edge silicon, advanced AI models would stall behind in progress. But something that those policies failed to consider was how computation itself does not have to follow this same digital path forever. Chinese researchers were asking a different question. While all these policymakers were tunnel-visioned on sanctions, the question was, what if AI's future did not depend on smaller transistors? What if the real breakthrough is not digital speed, but analog precision? Why digital computing is hitting a wall? One of the biggest obstacles in computing today is known as the von Neumann bottleneck, and that is also why digital computation is inefficient at scale. Training modern AI models requires trillions of matrix operations to happen, where each operation involves moving data from memory to a processor, performing calculations there, and then moving it back. This happens because the data is stored in memory, and the calculations happen separately in a processor. So this constant shuttling of data back and forth consumes enormous amounts of energy. Nowadays, modern AI is powered by digital processors that operate using binary logic. Every calculation is broken down into ones and zeros. Here, transistors have to act like tiny switches. Either they are fully on or fully off. This approach is extremely reliable, which is why it replaced the analog systems almost a century ago. But this reliability comes at a cost, and now modern computation has to pay that cost. This problem is getting worse as AI models are growing larger day by day. GPUs now consume hundreds of watts each, while entire data centers can draw as much power as a small city. The real limiting factors are heat dissipation, power delivery, and energy cost, but not the software innovation itself. Even if manufacturers somehow manage the nodes to shrink further, the gains will no longer be exponential, because physics is pushing back. This is the actual context behind Huang's warning. The current trajectory of digital computing can't scale further forever, because something has to change. It could be either in how we build chips or in how we define computation itself. the forgotten path of analog computing.
And on this analog computer, I can change the parameters and see their effects in real time. So these examples illustrate some of the advantages of analog computers. They are incredibly powerful computing devices, and they can complete a lot of computations fast. Plus, they don't take much power to do it.
Engineers explored analog machines before digital computing replaced them and became dominant. In analog systems, continuous physical quantities were used instead of representing calculation numbers as discrete bits. Voltage, current, resistance, and charge directly represented values in analog computing. In theory, this allowed calculations to happen in an instant, with the help of laws of physics rather than clock cycles. But analog computing failed in practice because small variations in temperature, material imperfections, and electrical noise caused errors to accumulate throughout the process, and precision degraded over time. Results became unusable after multiple operations, and that is where digital computing won. It replaced analog computing, not because it was faster, but because it was more stable in its operations. You can run the same calculator over 1,000,000 times, and you will get the same answer again and again without any error. Engineers accepted inefficiency of energy in exchange for reliability. It just became a fascinating idea that simply could not deliver the precision that is required for serious computation. This assumption held its place strongly until very recently, when China went on a different path. The breakthrough that changed everything. Researchers at Peking University, who challenged a century of conventional wisdom, published a paper in October 2025. They successfully demonstrated a precise, scalable analog computing system that used resistive random access memory, also known as RRAM. This was not any theoretical proposal or just a lab curiosity for fun, but it was actually a functioning chip that was built with commercially available manufacturing processes. The key achievement in this paper was not the speed alone, but also the precision. The researchers managed to successfully solve what had been known for decades as the only major fundamental problem of analog computation: error accumulation. This analog chip demonstrated precision that was equivalent to 24-bit fixed-point digital computation. This was the level of accuracy that was once considered completely physically impossible for any analog system. What is more surprising is how it maintained that precision across repeated operations. It is something no analog computer in history has ever achieved at such a scale. This effectively cracked a problem that had resisted solutions for over 100 years up until now. How RRAM changes the rules of computation. To completely understand why this matters so much, first, you have to understand how RRAM works. As we have discussed earlier, traditional memory stores data as binary states where a bit is either 0 or 1, but RRAM works in contrast with this and stores information as different levels of electrical resistance. In this system, a single memory cell can represent many values instead of just 2. You can think of it as a light dimmer that has many levels, as compared to a light switch that is either on or off. This allows computation to happen directly where the data is stored instead of moving numbers back and forth between memory and processor, as it happens in digital computation. Calculations occur inside the memory array itself in RRAM. When electrical current flows through the resistive cells, physical laws perform the computation naturally, which saves a lot of time and energy. This chip lets physics do the work instead of just simulating math step by step like digital computing. In benchmark tests, this analog RRAM system has achieved up to 1,000 times higher throughput than all the digital leading GPUs. It is something that has not been achieved with cutting-edge manufacturing nodes, but rather with mature fabrication technology that the West has largely ignored. Before we move on to US sanctions, take a moment to subscribe to our channel for more computation breakdown videos. Why sanctions didn't stop this. Several export controls were designed by the US to slow China's AI progress by cutting off its access to advanced chips, high-end GPUs, and advanced manufacturing equipment. This strategy assumed that without these tools, China would fall far behind and lose this race. But instead, the opposite has just happened. Rather than competing head-on in digital chip performance, they started focusing on alternative computing paradigms. Academic industry collaborations increased significantly, and governments raised their funding for these experiments and innovations. History has also shown this pattern clearly, where Chinese companies were placed on entity lists in the past, but they didn't disappear or accept defeat by it. But they actually adapted. Where domestic supply chains were strengthened, indigenous technologies matured faster than expected. The same dynamic is now playing in AI hardware. Jensen Huang acknowledged this reality and warned everyone that cutting China off from NVIDIA GPUs would only accelerate domestic innovation rather than suppressing it. This analog RRAM breakthrough is proof that this warning was not hypothetical. What this means for the AI arms race. Training of advanced AI models is not limited by algorithms anymore. It is now limited by energy consumption, infrastructure, and cost. This has changed the AI race from being about who has the fastest digital chips to who can compute most efficiently. Analog computing is attacking these constraints directly at their roots by dramatically reducing the power consumption. This system will enable AI training and inference to reach the scale that digital systems could not achieve. This will change AI economics entirely, where energy will become less of a bottleneck, deployment will be more flexible, and nations will gain a powerful advantage that has massive manufacturing capacity and strong energy infrastructure. Edge AI and the end of centralized intelligence. What this means for edge computing will perhaps be the most disruptive implication of this innovation. Digital systems rely on cloud infrastructure, where data is first collected locally, sent to centralized servers, processed, and then returned. This model creates privacy concerns, huge infrastructure costs, and latency. Analog chips will change that equation because their efficiency would allow advanced AI models to run directly on devices like smartphones, vehicles, drones, medical sensors, and industrial equipment. All these devices will be able to perform complex inference and even limited training locally without any cloud involvement in the process. This will enable a new generation of autonomous systems that would not depend on constant cloud connectivity. Why the West is unprepared. Despite these developments, most Western chip companies remain focused on incremental improvements to digital architectures, where roadmaps still emphasize smaller nodes, higher transistor counts, and faster clocks. These strategies do deliver diminishing returns, but they also increase complexity and cost. Radical alternatives like analog and photonic computing receive far less investment and attention in the West because they are often treated as experimental or niche. Meanwhile, China is pushing these technologies toward commercialization with a coordinated national effort. The future of AI will be decided by who values computation itself, not who has the smallest transistors. China has just shown that the old rules are no longer applicable in this race. If you enjoyed this breakdown video, then do subscribe to our channel for more AI and computing advancement deep dives.